Let's look at Unit 4. This is Antidifferentiation, so integral rules. So let me kind of go through integral methods priority order checklist. So when we see an antiderivative problem, we kind of want to have an idea as to how to work our way down to have a kind of a more organized method of deciding which rule is going to be most appropriate. So the first thing that we should always try is, can we simply expand the problem? Can we just rely on algebraic methods to clean everything up and then separate each into individual terms and then apply power rule? One way that we know we can do that is if we only see one term in the denominator. So it could be root x, it could be 4x, it could be 3x cubed. Anything that we can easily move up to the top. And also another indication is if their numerator has a degree that is 2 or less. And these are easily expandable. So always want to check first to see if our problem can be expanded before we attempt anything more complex like use substitution. So we should be able to tell by looking at a problem within a few seconds whether we can rely on just bring the denominator up and expanding. So that should be the first option. The second option is going to be use substitution. And use substitution is where we have a problem that's too complex or too where algebraically it's not possible for us to expand, like if we have multiple terms in the denominator. And that's going to cause us to look for ways to simplify the problem using use substitution. So the idea with use substitution is we're rewriting the problem using a different variable, and the hope is that we're able to create a form that matches one of our existing rules available. So here in this case we can't expand, so we will let the u value be x squared minus 2, and that will clean up the numerator and we can go from there. The next option is a use substitution problem, but then we have to go through another set of change of variable. We're going to see this later on in one of the examples, where our initial u value is not enough to remove the x. So if our u value is 3 minus x here, our derivative is -1, but -1 after we go through after we replace dx with du, we're not going to get this x to go away. So we have to go through another set of substitution where we have to rearrange our assigned u value expression to allow for x, to solve for x in terms of u. So we'll see one of those. The next option is looking to see if those options don't work out, then we want to look for maybe it's a long division or synthetic division problem. And a quick way for us to tell whether it's a long division or synthetic is if your numerator degree is the same or higher than the denominator degree of the highest of the variable. So in this case we can't expand because there's too many terms in the denominator, but this condition of having the numerator being the same degree if not higher than the denominator does stand, so we can go through long division synthetic. The next option down is maybe it's a arc-trig use substitution problem. And the condition is if your denominator degree, or if your denominator variable, is 2 or more degrees than your numerator variable. So here, x squared, let's ignore the fact that the square root over x of x squared is equivalent to x. Let's just look at the variable degree. If the variable degree is 2 degrees higher than the numerator degree, then that's a potential fit for arc-trig. Now this condition only applies something in rational form. So if it's a trig or exponential term, it may be an arc-trig problem, but it may not necessarily fit under this condition that I have outlined. We have another variation of arc-trig u sub where the degree of the denominator is 2, or where the variable in the denominator has a degree that is 2 more than what's in the numerator. But this is one that requires completing the square, And we'll see an example of that where we are going to use our trig, but it's not quite set up for us to move forward with use substitution. So we'll see one of those. Okay. Let's look at number one. So number one, we have a binomial squared, and anything that's binomial squared is manageable enough to just simply expand. So let's rely on that. Just because we see parentheses doesn't necessarily mean that we have to go into something more complex like use substitution. So I'm going to FOIL this out, expand this out. So I get x squared minus 1/2 minus 1/2 plus 1/4, 1 over 4x squared. Okay, so we have every term separated by either plus or minus, no parentheses getting in the way. Combine some like terms. So I'm going to rearrange this to be x squared plus 1 over 4x to the negative 2. So I know that I want to try to get every term ready for power rule. So I just have to combine the like terms here. Here I can move the x squared up to the top, but keep the 1/4, keep the 4 in the denominator. So in this form, now I have something that is able to be done. We have power rule. Every term is set up and ready for power rule. So with power rule, we add 1 to the exponent divided by that same exponent value. So x squared becomes x cubed over 3. For the second term, the 1/4 is the coefficient, so it stays. X to the negative 2 becomes x to the negative 1 over negative 1. And minus 1 becomes negative x. And then this is an indefinite integral, so we have a plus c. We have our antiderivative. We just clean this up a little bit here. I'll move the x down to the denominator. I'll make this a negative 1/4. And my answer choice doesn't match any of these. So here's the correct antiderivative, but it doesn't match any of the existing answer choices. So our E is our answer. Right, number 2. We look at our problem, we look to see, can we expand this, but notice that there's too many terms in the denominator. The square root is not suitable for us to distribute and simplify the way it is, so it kind of has stuck in this form a little bit. So let's look at use substitution. So for use substitution, I always want to see if I can identify a parentheses to look at. If I can identify a set of parentheses, usually what's inside the parentheses is a good start for a potential u value. So I see the denominator has a square root. I'm going to rewrite that square root as parentheses to the 1/2. I'm kind of expecting this could be a u substitution, but maybe a power rule problem later on. I'm going to move the parentheses up to the top, make it parentheses to the negative 1/2. Okay. We'll let the parentheses, what's inside the parentheses, be our u value. So du over dy, 2y becomes 2, 3y squared becomes 6y. We cross multiply, we get dy is equal to du over 2 times 2 minus 6y, which I can factor as 2 parentheses, 1 minus 3y. So I have a substitution for my parentheses, I have a substitution for dy. I make those substitutions back into the problem. So this set of parentheses stays. This turns into a u. The dy becomes du over 2 parentheses 1 minus 3y. Our goal is to get rid of the variables that's not associated with u. So in this case, we want to replace the y. And we see that we have a nice factor that we can take out for these parentheses here. Then we can push the 1/2 out in front. This is a nice setup for power rule. We then apply power rule. We add 1 to the exponent, divided by that new exponent. And then we have our antiderivative. We just want to be able to get this in terms of our original variable. So I'm going to clean this up here, flip that 1/2 up as 2 over 1, cleans that up, replace the u back in terms of our original variable, which was y. And answer choice E.